I said, number 16, can an altitude of a triangle also be a median of a triangle? I said yes, as long as it's isosceles. So here's my isosceles triangle. I know that my two legs are congruent. Well, if I draw in that median, then it goes from vertex to the midpoint. So that's why I know these two segments are congruent. So now I can show that that also has to be the altitude. What do I have to prove about this diagram to show that this truly is the altitude?
It has to be perpendicular.
It's got to be perpendicular, okay? Because it goes from vertex to the opposite side and perpendicular. So if I can somehow show that that's a 90-degree angle, then we're in business. So I can prove that these two triangles are congruent by what? Side, side, side. Okay? That means using CP/CTC that the corresponding parts are also congruent. That's why I know that this angle is congruent to that angle, because those are corresponding angles in these two triangles. Well, those two angles form a special type of pair. Together they form a linear pair. Well, if two angles are a linear pair, then by definition of a linear pair, they're supplementary. The only way you can have two congruent supplementary angles is if they both equal what? 90 degrees. So you know that the measure of each of those is equal to 90 degrees, therefore they are right angles. So if you have an isosceles triangle and the altitude is coming from that vertex angle, it's coming from the vertex angle, then yes, a median will also be the altitude. This segment here is the median, it's the altitude, it's also something else. It's the perpendicular bisector, right? It's the perpendicular bisector of this side here. Is there anything else? There's only one more. The angle bisector. Is it an angle bisector? Yeah. CP/CTC. Those are corresponding parts in those two triangles. So that segment, if you happen to have the segment drawn from the vertex angle of an isosceles triangle down to the opposite side's midpoint, it's the perpendicular bisector, it's the altitude, it's the median, it's also the angle bisector. So yeah, if the triangle is isosceles, that was number 16 on page 197. Number 20. If the length of segment EU is 8, so I'm going to go ahead and mark my diagram. If this is 8, then the length of segment UY is what? Well, it tells me that point U is the centroid. Point U is the centroid. What three special segments intersect to create the centroid? The medians. So I know that the median connects vertex to opposite sides midpoint. So I know that E is a midpoint, I know that T is a midpoint, and I also know that S is a midpoint, because those are my three medians. They intersect to form the centroid. But we also know some information about the median's lengths when you have the centroid that's introduced. The centroid breaks the median into two parts. One is 2/3 of the whole length, and then the other portion is 1/3 of the whole length. That works for every single median and every single triangle when you have the location of the centroid. The centroid will always break up a median into two parts. One part is 2/3 of the whole median, and the other piece is 1/3. So what we're given is the smaller piece of this whole median. And so the centroid creates segment EU and segment UY. Those are the two pieces of the whole median. So I know the smaller portion is 1/3 of the whole, and I know that the larger portion of the median is 2/3 of the whole. What's the relationship between the two pieces? This segment, how is it related to this segment? It's half. So that's how the pieces relate to one another. So if this segment, E to U, if that distance is 8, then what is the length of segment UY? 16. You just double it, right? Because that's how these two are related. So it is 16. Then it asks for the length of segment YE. That's the whole thing. There's two ways of solving this. You know that you were given 1/3 of the whole thing. You were given a third of the length of segment YE. So you just take 8 and multiply it by 3. And that'll get you the whole thing. Or what's the other way that you could solve this and get the correct answer? That is 24. What's up?
16 and 8.
Right, you can add the two parts together because we just solved that was 16. So 16 plus 8 will get you 24. Same thing as 8 times 3 is 24. So a couple of different ways to go about that problem. But it all boils down to you knowing the relationship between the centroid. How does that affect the median? Well, it breaks up the median into two parts. Breaks the median up into two parts. One is always going to be smaller than the other. The smaller one is a third of the whole. The larger piece is 2/3 of the whole. How they relate, how those two pieces relate to one another is that the larger piece, that will always go from the vertex to the centroid. That larger piece is twice as long as the smaller piece that goes from midpoint to centroid. All right, we'll move on to the next page, page 200. First, you were assigned on page 200, 12 through 19. 12 through 19. So, these problems, 18 and 19, those are extremely similar. I'm only going to do one of those. We'll take a class vote of which one we want to do. Let me first answer questions on the ones that came before that. So that would be 12 through 17. What questions do we have on problems 12 through 17? What's that? 17. Number 17. Number 17 says that if the measure of angle CAB is equal to 90 degrees and the measure of angle CBA is 25, and what are the missing angle measurements that they have? Well, first let's look at the instructions. It says that we are given triangle ABC, so that we're given this triangle with in-center D. With in-center D. Before we start trying to solve this problem, we need to think about what's the significance of having the in-center. First, what special triangle segments come together to form the in-center? The angle bisectors. So the three angle bisectors will intersect to create the in-center. So that's why I know this segment here, and that segment there, and that segment there. Those are the three angle bisectors. They obviously all come together and meet at that in-center, and they're coming from the three vertices. So these are the angle bisectors. Sweet. Now another thing you need to know, and you need to have memorized for the test, is what's so unique about the in-center? How does it relate to the triangle? It's always on the inside. What else? Yep. It is equidistant from each side. And that length needs to be the perpendicular distance. That's why I know that the length of segment DF is congruent to the length of segment DE. Because the in-center will always be equidistant from the sides. But you need to make sure that you're talking about the perpendicular distance when you're talking about the distance from a point to some object, whether that be a segment or a ray or a line or a plane, whatever. Alright, so let's start marking up this diagram. Apparently, we know that the whole measure of angle CAB is 90 degrees. So I'm just going to put in a right angle marking in there, and I know that that measure of angle CAB is 90 degrees. Then they give us that the measure of angle CBA, so this guy right here, this whole angle, is equal to 25 degrees. And we are tasked with finding the measure of angle CBA. Well, then we just need to look at this large given triangle, triangle ABC. What theorem are we going to apply to solve for the measure of this angle here, angle ACB? Triangle sum theorem. And that theorem states that the three interior angles, their measures will sum up to be 180 degrees. So 90 plus 25 plus what is going to get you 180 degrees? You should get 55, 65, Sorry,
Correct.
65 degrees. Alright, so we've got that one, just using the triangle sum theorem, that the measure of angle ACB is 65 degrees. Now we are asked for the measure of angle ACD, which is this guy right here. How am I going to find that? Divide by 2. Right, because this is the incenter. The incenter is created by your angle bisector. So this whole angle that we just found that was 65 degrees, it's being bisected by a line blue segment here. So half of it is going to be 32.5. Number 13. Number 13 says, draw 3 sketches showing the circumcenter lying inside, outside, and on the triangle. Make conjecture about the location of the circumcenter and the type of triangle. On your point of concurrency notes, I tell you that this circumcenter can be inside, on, or outside the triangle. And so what happens is you've got 3 different types of triangles. You've got your acute triangle. So here's a quick sketch. Now, it says to draw sketches with the circumcenter. You need to know what the circumcenter is created by. Which special triangle segment creates the circumcenter? The perpendicular bisector. The perpendicular bisector. So I need to draw in the perpendicular bisector. So first, I got to find my midpoint. So that's about the midpoint. That's about the midpoint. And that's about the midpoint. So my perpendicular bisectors would be right here and right there and right there. So when you have an acute triangle, those perpendicular bisectors are going to intersect inside the triangle. And that's where my circumcenter would be for an acute triangle. Let's talk about a right triangle. Those are my midpoints right there, about-ish. Now I'm going to draw in the perpendicular segment. So this guy right here is perpendicular to there. This guy right here is perpendicular to there. And then this guy right here is perpendicular to there. So this is where the circumcenter is actually on the triangle. It will be at the midpoint of your hypotenuse. Your circumcenter for right triangle is always on the midpoint of your hypotenuse. That's where they'll intersect. So this is an example when it's on. Then the last one is obtuse. Bless you. Here is an example of an obtuse triangle. So same thing, I'm going to find my 3 midpoints. And again, these are just sketches, so I'm not really taking my time on these. And then drawing in those perpendicular segments. There's one right here, and there's one right there, and then there's one right there. I want to be extremely detailed. I can add my marks of congruency and just saying that hey, these are the midpoints. But this is an example when that circumcenter is going to be outside of the triangle. So the conjecture that you would make about the type of triangle and the location of the circumcenter, it's already printed on your point of concurrency chart. And if you have an acute triangle, that circumcenter is going to be inside. If you have a right triangle, it's going to be on. If you have obtuse, it's going to be outside. What other point of concurrency works this way? The orthocenter works this way as well. The orthocenter, that's the point of concurrency for your altitudes. If it's an acute triangle, your orthocenter is going to be inside. If you have a right triangle, your orthocenter will be on. But for the altitudes, it's the vertex of your right angle. That's where it's going to be on that right triangle. Or sorry, on that right triangle. And then if it's obtuse, that orthocenter is going to be outside. But it's not going to be where the obtuse angle is opening up. Your orthocenter is going to be actually on the other side. Your orthocenter is going to be on the other side of the triangle. It's going to be out this way.